Log on, tune in, find out. Another good idea from Cambridge.
Welcome. It's my great pleasure to welcome Friedrich Knop, who will tell us about the representations of ST when t is not a natural number.
Okay, thank you for the opportunity to let me speak here. And first let me explain a little bit what this talk is going to be about. It is about a tensor category which you can think of as the category of representations of a symmetric group in T letters, but now T can actually be an arbitrary complex number. This category has been constructed in a paper by Deligne of approximately 2002. And the main topic of my talk is to generalize this construction, and also to say something more about this Deligne's category. Now, I've given this talk in the last 2 years or so several times, and once somebody asked me at the end whether this theory brings any new results on actually representations of Sn. Well, it's I must say it's terribly hard to find anything new on representations of symmetric groups. Therefore, the answer is strictly as no. But at least I found some new approaches, as I thought, to some results of Sn. And then, just recently, I learned that it seems that Littlewood knew all these arguments also very well. And now I at least understand Littlewood. Okay. Now, this category has 2 origins. One of them is, you could say, stability of rep Sn as n goes to infinity. Then it's well known in many formulas and many results that as n goes to infinity, certain things get stable, and dimensions become polynomials in n, and so on. This has been used over and over again, and gives rise to the philosophy that you should never study representations of the symmetric group, span group at a time, but you should study them simultaneously. And this construction now gives a new emphasis on this philosophy. Therefore, that is one thing. This category of Deligne is basically what's left of rep Sn as n goes to infinity. And the other one, origin, is sure-while duality. And for this, you take the defining representation of Sn, and take now the, let's call it this m here for the moment, as Cm, and take the n-fold tensor power, and then Sm will act on it, and you can try to compute the endomorphisms, the Sm endomorphisms of this. This has been done by independently by Jones, Vaughan Jones, and Paul Martin. And what they got is a so-called partition algebra, P, N, M, M, N, whatever. And I will explain that in a moment. This partition algebra business is now a little industry with something 30-odd papers, and there's a very nice survey paper by Aaron Ram and Tom Halverson. And there are many generalizations, a couple of generalizations of these partition algebras, where you can repeat all these arguments, and this kind of zoo is now unified by this generalization which I'm going to present. Okay, now let's start. Let's start for simplicity with a finite group G. By the way, all representations will be over the complex numbers. And we want to construct the category of representations of G, of finite dimensional representations of G. What you do is we choose a faithful representation V of G, and then it's known that if M is simple, a simple G module, then there exists an N bigger or equal 0 such that M is inside some tensor power of V with itself. It's easy to prove. And therefore, since G is finite, reductive, it's even a direct summand. Therefore, every simple module is a direct summand of a tensor power. Therefore, every finite dimensional module is a direct summand of a direct sum of tensor powers. And therefore, from a category theoretic point, all you have to construct is basically just this subcategory whose only objects are these tensor powers. Okay, therefore, let's say rep 0 of G, that is the full subcategory with objects b to the power n, tensor power n. And now the objects are very simple. They're parameterized by natural numbers. Now we need, for the construction of the category, for the description, we need also the morphism spaces. Therefore, we have to compute what is Hom G, V tensor n, V tensor P, V tensor Q. Let's call this MPQ. These are certain C vector spaces. And now to get the category completely, we need also how to compose morphisms. That means we need to know the composition map from MPQ, MQR to MPR. Okay. Now this looks very pedestrian, but that's actually what how many physicists are working with groups, especially with SU2, yeah, where, for example, these kind of laws are encoded in the so-called 6J symbols. Therefore, if you really want to have numbers at the end, you have to do something like that. Okay. Now we do that for Sn. Therefore, now G is Sn, and V is just C to the n. And I'm thinking of C to the n as the functions on the set bracket n. And bracket n is just the numbers from 1 to n. Okay, and these are just functions, C-valued functions. Now, this representation has the nice property that it's self-dual. And this means that Hom Sn V tensor P, V tensor Q is actually the same thing as the fixed points in V tensor P plus Q. Okay? Therefore, you have one parameter less. Now we describe this here. Now, what is V tensor M Sn? Well, these are the functions on this set bracket n. Then of this function space, the mth tensor power, and here the fixed points. Well, from algebraic geometry, we know this is just the same thing as functions on the mth Cartesian power of n with itself, and here fixed points. And you can write this also as functions. These are just maps from the M or a set of order M to the set of order N. And here Sn. And now we do a little bit of invariant theory. The invariants on a set are just the functions which are constant on the orbits, and therefore this space is generated by functions, or it's the same as functions on the quotient. More map modulo Sn. Okay, what you're doing is you're taking maps from m points to n points, but you are allowed to permute the target. Okay? Now if you have this, then such a map is just given, is known if you know the fibers. Yeah, because you do not label anymore to which point they go. Therefore, now if you know the fibers, then the fibers, if you just throw out all the empty fibers, they partition the set of m elements into at most n sets. Therefore, this is the same as functions on the set of all partitions of the set M, but with the proviso that you have at most n parts. Okay, and now the actual point for the stability here is now just the observation that if m is smaller or equal n, then a partition can't have more than n parts. Therefore, this condition actually is superfluous. Therefore, we get and that this is just partitions of m under the condition that n is sufficiently big, namely in this case n is bigger or equal m. And then this here is completely independent of n. Okay. I mean, that's in a nutshell why the representation theory of Sn becomes stable. Okay. Now, where does the n come in? Actually, we still have to compute this composition. But before I do this, let me give you just some example what that actually means. Let me get over here. Yeah. Okay. If we have a partition, to every partition P, there corresponds now some tensor in V tensor M as Sn. And how does one do that? For example, if I have the partition 1, 4 points, and I have the partition, say, 1, 4, and 2, 3 lumped together, then this corresponds simply to the tensor EI, tensor EJ, tensor EJ, tensor EI, and the sum over all I and j. Okay, and you see that whenever two positions here are in the same part, then they're going to have the same index, and that's correspondence. And if you now observe this and also observe how this self-duality works, then you can compute the composition of two such phi p, and you get the following. Probably you have seen this similar pictures already. Namely, let's say this here corresponds to the set bracket 4. And now I have a map to bracket 4. And therefore, we need a partition of these 8 points. That's what what we need. And here, for example, I take this partition. These two belong together, and this belongs together. These two belong together, and these three also belong together. Okay. Now I want to compose that with a diagram for with a partition from bracket 4 to bracket 3. You see, it's not very deep. Here, took this. Okay, a partition in 3 parts. And what you're doing is now you just identify these points here, and then you get a map from bracket 4 to bracket 3 by still lumping together this guy, 3 and here, and this is going to be here and here and here. Okay, if I'm not mistaken. And finally, you also have here this loop floating around, and the loop simply means that you have in there a sum I equals 1 through n, ei, comma ei, and now you take the inner product of these two. Okay, that corresponds to a loop, and this is of course n. Therefore, the composition of this partition with this partition is this partition times n. And the idea is now, which is not new, to replace this n by just the parameter t. Okay, this has been done already by Martin in the very first paper on partition algebras. If, by the way, if you have if the range and the domain are the same, then you get endomorphisms of a tensor power, and these endomorphisms are called the partition algebras. Then you get exactly this PMN up there. Okay. Now, now we define the following category after Dulin. We have 0 ST. It has as objects just symbols bracket m, where m goes to 1 and so on. Therefore, I do not think of these as sets anymore, but just symbols. Morphisms from P to Q. These are just C-linear combinations of partitions of the disjoint union. And now I'm, well, basically of the union of P and Q, right? Let's write it like that. And the composition is just as described over there. I'm not going to make this formal because I'm going to do that formal in a moment. But you just take, therefore, if you have phi p and phi q, then you have this phi r. And here, instead of n, you write always t. And here t to the L, and L is the number of loops which you get in this construction. Okay? Now, because if when t is any natural number, then you actually get the composition of real existing maps between Sn modules, and that means that this composition here actually is associative for natural numbers, and therefore because they are Zariski dense, it is associative in general. Okay, therefore we get actually a category this way. And by the way, this is a tensor category by where the tensor product is you take just a bunch of dots, then another bunch of dots, and put them next to each other. And now rep ST without the zero is what is called the pseudo-abelian closure of rep 0 ST. In other words, what you're doing is you take in a formal way all finite direct sums of objects of this form, and then you take in a formal way all direct summands. And that you can do because the direct summand is encoded inside the endomorphisms, which you know, as an idempotent. Therefore, idempotents give you direct summands. Now, the theorem of Deligne says the following. Let T not be a natural number, then this category rep ST is a semi-simple and therefore abelian tensor category. I think that was actually the main objective of Deligne, as far as I understand it, to construct some a tensor category with all the bells and whistles. That means you have associativity, symmetry, you have rigidity, everything, okay, which is not Tannakian. This is not a Tannakian category because the dimension, the internal dimension of the object 1 is T. Yeah, the dimension of an object is the trace of the identity, and the trace is just a number, and there can be any number. Therefore, if T is not a natural number, this can't be Tannakian. Now, since this is a semi-simple tensor category, you might ask, what are the simple objects? Now, the simple objects are parameterized by Young diagrams. Remember the simple objects of of rep Sn are parameterized by Young diagrams with n boxes, but here is no constraint. Okay, these are just any number of boxes. So now I want to generalize this and make it, at least for me, it became then much clearer what's going on. We now rephrase everything in a category theoretic language. Well, in this case, a partition is nothing of a set S. Is nothing else than a quotient, or to be more precise, a quotient object. Okay? You have sub-objects, but you also have quotient objects. And partition is nothing else than what you would call a quotient object. Now, a partition of a map from S to T is now a partition of the disjoint union of S and T. I think of S and T as dots. Okay? And therefore, you have a map like this, which should be surjective. But you don't even need this disjoint union sign. What you have is a diagram like this, which is jointly surjective, which means that the union of the images of S and T and P is everything. Okay? Therefore, jointly surjective. And now the composition becomes now following diagram. You have three sets, S, T, and U. You have a partition of S union T. Let's call it R. And then we get a jointly commutative surjective pair of arrows like that. A jointly commutative arrow like this. And how to compose these two? Well, if you trace through all this, all you do is you take the, no, this is not good, P and Q, I'm sorry. P and Q. You take the push out R of this diagram. In other words, you take the disjoint union of P and Q, but then you identify all points which come from the same point in T. You might have to do that several times. It's on a computer, it's actually not so easy. You have to go through zigzags. But anyway, this is a push out. The problem with the push out is that the outer maps from S or U to R are not jointly surjective anymore. There might be points which come through only from T. Therefore, what I'm doing is I take the common image R0 of S and U such that R0 is just the union of the images of S and U. Okay? And now the composition is simply phi P times phi Q is phi R0. And now the points which are missing, these are exactly these loops. They are living only in the middle part T. Therefore, this is T to the number of elements of R minus R0. Okay. Now this way, it's also still a little bit difficult to understand what's going on. Therefore, I think the only thing where I claim some originality is now to reverse all arrows. In other words, we are now working in the category of, which is opposite to the category of finite sets. Well, then we get actually very familiar objects. And now I'm also changing notation. My objects in this new category I denote by lowercase letters. Therefore, a partition which corresponds to a partition from X to Y corresponds now to a diagram R from X to Y, which is jointly injective. In other words, R is just the subobject of X cross Y. Now this is classical, it's called a relation. Therefore, what we are doing here is what one could call a correlation in the category of sets. Now I'm doing the relations in the opposite category of sets. By the way, this is also the equivalent to the category of Boolean, finite Boolean algebras. Therefore, this is something which is real. Okay, this is the relation. And in the very first category theory paper by McLean, he constructed already a category of relations. as an example of a category where the morphisms are not maps. Therefore, this construction lies at the very beginning of category theory. Now, the composition is now following. You take x, y, z. You have two relations R and S between x and y, respectively y and z. Then you take now the pullback T. And now, instead of taking the image, I'm now taking the image of T in x cross z. Let's call this T0. The image of T in x cross z. Then we have a new relation. And this is called the product of R and S, R circle S. Now, that's the product of two relations. So that's classical. Less classical is now the factor which is still in here. Okay? We have to insert this. Therefore, I'm now extending the theory of relations by a little factor. I want, at the end of the day, I want to have that R times S is equal to some number times R classical relational product. Now, what should this number be? Well, this number is basically tells you how far this morphism here is away from being an isomorphism. Now, this is subjective by construction. Therefore, let's call this E. And this number will depend only on this E. And in the same way as this number up here, T to the depends only on R0 included in R. And to make this associative, it's a matter of a couple of lines to work out exactly the conditions on delta which had to be satisfied. Therefore, definition, delta is now a map from all epimorphisms, and now we call A the category fin set op to C. It's a map with three axioms. First of all, delta of the identity is 1. Then you should not have a factor if this map is actually an isomorphism. Second, delta of two composable epimorphisms is just the product of the deltas. And 3, and that's the most complicated part, is that delta commutes with pullbacks. Therefore, if you have a pullback like that, x, y, x, the vertical arrows, this vertical arrow is arbitrary, but this here is surjective, then this is going to be an epimorphism 2, E bar, and then I want that delta of E bar is equal to delta of E. That's what you need. And if you go through through this particular category, then you see that the only degree function is delta, well, of A. Injective maps are now the epimorphisms. That is T to the number of elements in the complement. That's the only possibility. Okay, that's pretty easy. But now it's kind of obvious how to generalize this. I already wrote here A. I want to replace the category which is opposite to finite sets by an as general category as possible. Now for that, first of all, in this category, there should be all the ingredients which you need to have the classical relational calculus. And this has been already worked out by Michael Barr in 1970. And he came up with the notion of a regular category. A regular category is one which has all finite limits, in particular direct products and a terminal object, which is the empty finite limit. Second, it also has images. Every morphism has an image. In other words, for every morphism, there's a smallest sub-object of the target, which through which your morphism factors. And the crucial property is now that images, or equivalently epimorphisms, commute with pullbacks. Okay, therefore, let me see. Okay. Let me say, let's do the same diagram as before. This is a pullback diagram, commutative diagram, and this here, E is an epimorphism. This should imply that E bar is an epimorphism. Okay, so for example, a typical category which is not regular is the category of algebraic varieties. First of all, it doesn't really have images, but even if there is an image, I mean, the image is then usually just an open subset, say, and if this is just one point, then even if this is surjective in a variety sense, then you might just miss exactly the point which is not in the image. Therefore, there are usually geometric categories are not regular, algebraic categories are regular. Category of groups, category of lattices, category of posets, category of algebras, rings, these are all regular categories. Okay, and having said this, we can now define so therefore, if A is a regular category and delta is the degree functions on epimorphisms, then we can define first category which I call TA delta, T0A delta, where the objects are exactly the same as the objects of A, but the morphisms are relations, C linear combinations of relations, and composition is just what I wrote down here. That is the composition of two C linear relations. And then we take the pseudo-abelian closure, and I get TA delta. Okay. And let me give you some typical examples. Then, as I said, if you take A equals fin set op, then you get the endomorphism rings are now the partitions algebras. Okay. some endomorphisms rings are partition algebras, as explained before. Now you can take as A also so-called diagram algebras. That means you take one fixed category, pretty small, and take all functors from this category into a given category which is already identified as regular. That is going to be regular again. And therefore we can take, for example, as category all arrows in fin set. But then we take again the opposite category of that. Okay? And then the endomorphism ring becomes something which Martin baptized ramified partition algebras. Okay. Then you can also take the category of all three G sets. G is now your favorite finite group, and you take the category of three G sets. This is not quite regular. You have to fudge around a little bit because there are not all finite limits there, but the opposite category. But you can deal with that. And then you get what is called the so-called G-colored partition algebras. And if you are more exotic inclined, you take A to be the category of all finite abelian groups. No, not the opposite of that, but just the category of finite abelian groups. Then actually you get, at the end of the day, I will not come to this, back to this, the category of representations, which is the representations of GLT with values in Z hat. All finite dimensional continuous representations of this non-existing group. Okay? And now finally, and that was actually my main motivation, one takes the category of all FQ vector spaces. And then you actually have a model for the representations of GLT FQ. That means the size of the matrix can be interpolated. That brings me to the one unsolved problem in this obvious problem in this business. Can you interpolate also the Q in there? Everybody wants to do that and then put Q equals to 1. Yeah? But I cannot do that. I mean, this is still just, as far as I know, philosophy, that if you do GLNFQ, where Q is 1, then you actually get Sn. Okay. But at least the size of the matrix I can interpolate. Okay. How much time do I have? So, now you want to say something. Excuse me?
The right side is only defined that way, or is there?
Yes, it's defined. Well, they actually functors. If you take web, for example, GLTFQ, that's a category which depends on this parameter T. Okay. Now, if you plug in T equals Q to the N in this case, the notation is really bad. Now, let me try T equals N, then you get actually a faithful, a surjective sort of morphism to GLNFQ. You get comparison morphisms for every N. But this category has much more objects and much more morphisms, and some of them are just mapped to 0. And it's not easy to control what exactly is mapped to 0. It's a kind of a radical the so-called tensor radical, which you have to mod out. Yeah?
Do you have a way of writing generators and relations for these on the
In this generality, not, because you really have then to write generators and relations
What
for.
about for GLP or
Yes, yes. There it is possible to do that. I come to this in a moment. Now, in general, it says no chance whatsoever that you can say anything good about this category. For any, you need some conditions on A, but as we know in Deligne theorem, you need also conditions on T, some non-integrality condition. Now,
Is it possible to recover the category of GLT by a sort of limit, or when you make to vary n on the right hand side? Yes, is there a sort of a system when you make n to vary, which you see there is a kernel?
Yes. I mean, Deligne mentions that in his paper. You can actually do this by starting with these categories on the right-hand side, takes their direct product, all of them, and take a so-called ultra filter in there, and mod that out, and then you get. But you have to choose the right ultra filter for this to work, and it's not very explicit. But theoretically, you could do that, yes.
I'm confused. Aren't you only getting uniform representation of GLN?
No, because whenever you have a faithful representation of a group, then the tensor power eventually contains every representation. Okay. Please keep in mind I take really, really huge tensor powers and keep the dimension fixed. Or is it the other way around? Whatever. Anyway, we need conditions on the, and then we get the following theorem, which I have to cut a little bit short, namely assume. So first a condition on A. A is, the first condition is very easy to explain. The relations between, therefore the subobjects of x cos y are a basis of the morphism rings. Okay? Now, to have something semi-simple, in particular the morphism spaces should be finite dimensional. And therefore I want to have that every object has only finitely many subobjects. Okay, that conveniently is the case in all these examples because these are just finite structures. Therefore, I'm looking only at finite structures, finite groups, finite rings, finite whatever. Second, and now we're becoming a little bit more category theoretic. A has to be exact. That's also quite easy to explain. In a relational calculus, you also have the notion of an equivalence relation. That's something which is reflexive to symmetric transitive. And then you can try to find the quotient of an object by an equivalence relation. That's some co-kernel thing. Yeah? And if that always exists, then you have an exact category. For example, the category of torsion-free abelian groups is not exact because, but it's irregular. So, and now comes the most difficult to understand condition, namely A is also the so-called Maltsev category. That is a category which has a funny property that every reflexive relation is already an equivalence relation. You might ask, does it exist at all? Well, it is has been observed by Goursat, implicitly of course, that the category of groups has exactly that property. Therefore, I leave that as an exercise for tonight, that you have a group, you have a subgroup H, and which contains the diagonal. Then H is considered as a relation on G, an equivalence relation automatically. These categories are called Maltsev. And basically, Maltsev is very close to having a group structure involved. For example, the category of rings is a Maltsev category because you have the addition. Yeah? Every ring is a group, a building group. And for those who are teaching algebra, higher algebra, if you come to the point proving the Hölder-Jordan theorem, okay, there's always the strange thing that somehow the Jordan-Hölder theorem always works, but you don't know why. You always have to give separate proofs for rings, for modules, for groups. There are certain workarounds, but now I can tell you the category of the class of Maltsev categories are exactly those in which the Jordan-Hölder theorem holds. Okay. Okay, and then we need also that some numerical condition, since I'm almost out of time, on delta, which then for the category of finite sets op boils exactly down to the condition that T is not a natural number. Then TA delta is a semi-simple tensor category. Moreover, the simples the simple objects are parametrized by, my handwriting deteriorates, by pairs x comma pi, where x is an object of A, any object of A, and pi is an irreducible representation of the automorphism group of X. Do that for fin set op. The objects are, this is all in pairs up to isomorphism. So your objects are up to isomorphism just finite sets. The automorphism group are the symmetric groups. Therefore, you take all representations of all symmetric groups simultaneously. That's what it says. In other words, if you take the Grothendieck group of TA delta, that's a ring because it's a tensor category, that is canonically isomorphic to the direct sum of all representation rings of all automorphism groups of objects. Therefore, that's what you should study simultaneously. Take FQ vector spaces. You should study all GL and FQ for all n simultaneously. Old thing. Lewinsky did this already. Okay? Not so old. Study all representations of the automorphism groups of all finite groups simultaneously. This has not been done as far as I know. It's probably an impossible task. But for example, you can also study all representations of all automorphism groups of all finite abelian groups simultaneously. Okay. What? Now I have to. Now I would like to give some flavor of results which you can prove about these categories, and then you actually, if you specialize, you get results about the category of representations for Sn. And one of that is one would like to know, you know the simple objects, now you want to compute the tensor product of two simple objects. Therefore, let's call this one simple object parameterized by, say, x1 and pi1, and you want to take the tensor product with the one corresponding to x2 pi2, and to make it more symmetric, what I'm going to do is simply I take a third simple object and look at invariance, at fixed points in there. Category theoretic, this simply means that I take all homomorphisms of the unit object, of the trivial representations, into this. So what is that? And there's actually a theorem giving you a complete answer. This is a big direct sum of all hom A of R no, do I want to write it that way? Actually not. You take pi1. This is actually a representation of a known finite group, right? The automorphism group of x1. Therefore, it acts on some vector space, and I identify pi1 with its vector space. Therefore, I take now the tensor product of these three vector spaces. And later on, some group A of R will act on this, and I take the fixed points. And that is what the direct sum is over. So what is R and A of R? Now R runs through all subobjects of x1 cross x2 cross x3 modulo the automorphism groups out x1 cross out x2 cross out x3. Let's call this group here A. Okay. Not yet done. A of R is a stabilizer of, let's call it an A sub R. A of R, A sub R is the stabilizer of R and A. But that would be too much. We take only a very special kind of subobject, namely the three projections to one factor. They are also all surjective. And if I take the projection to two factors, they are all still injective. Well, that's the result. Okay. I mean, this on the right-hand side, this is just a finite group business. A of R is A sub R is a given finite group. Now, if you apply this to fin set op, you get the following. You have three sets, namely x1, x2, and x3. x1, x2, x3. And they are now being mapped to a set R. Now I'm now reversing all arrows here. Now this here means that all these here, they're actually all subset of R. And this condition here means that every point of R is contained in at least 2 images. There's not a point which is only contained in the image of one of these sets. I'm sorry. And well, in particular, there are not so many possibilities, but in particular, it might happen that these 3 sets here have an intersection in R. Okay? Certain points have come from everything. And if you now unravel all the definitions and everything, you get a formula of Littlewood. And I think one should also include Monachan, who detected this phenomenon, about the stable, so-called stable Kronecker product of representations. I may have 3 more minutes to explain this. Okay. The thing is, the usual Kronecker product means that you have S lambda, a Schur function, and another Schur function of the same size. And the Kronecker product of these tells you how the tensor product of the corresponding Sn representation decomposes. Okay, it's a very difficult problem. Algorithmically not so easy. And now what Monachan observed is that these multiplicities do not really depend on the first part of lambda or mu. That means if you take now just 2 partitions lambda and mu of arbitrary size, then you can make them to size n, if n is big enough, by just adding a first row. Okay? This is just n minus lambda, lambda. Now you take the Kronecker product of these 2, which depends a priori on n, decompose that, then you get some multiplicities. Let's call them m lambda mu tau of n as tau n. And the observation is if n is big enough, which can be made precise, then actually these multiplicities here are independent of n. And now you make a new product. You simply say S lambda star with a circle around it, S mu, is exactly some m lambda mu tau S tau. And here, with this new product, the degree of the Schur function doesn't have to be the same. And now, this formula here, specialized to the case of fin set op, gives now, after maybe 10 lines of calculations, easy calculations, the following formula. S lambda star S mu is the sum over all alpha, beta, gamma. These are partitions. Alpha and beta should have the same size. Then I take just the Kronecker product of S alpha and S beta, the usual one. And then here I take S lambda over alpha, this Q tableau, alpha gamma times S mu over beta gamma. That's the formula of Littlewood. And actually it can be used. I mean, who is interested in this? It can be used then to actually calculate Kronecker products recursively. Because actually this formula T is also valid if you just give these symbols here special meaning. This is a so-called modification rule, which you have to apply, and therefore actually the stable connector product gives you in turn again the usual connector product, and since alpha and beta are smaller than lambda and mu, you get a recursion formula. And I still don't understand it quite, but I have the sneaky feeling that in this line of argumentation basically was Littlewood's original proof. Okay. Even though this has been now, I mean, experts in the field say this proof is not quite rigorous, but I'm not the person to judge this. There's a paper by Cummings which proves this formula really rigorously, but with different, much more computationally means.
Questions?
And when you take C, it can work over a finite field, a priori.
Then you get something very complicated. Of course, that has to be worked out. You get a priori a formula for the tensor product of two simple modules of GL and FQ. But the ingredients for this formula are very difficult. But it can be done. I mean, basically, the ingredients are you have the product of three GLNs, and then you have certain subgroups, basically GLNs with some unipotent groups. Then, and all you have to know is how representation restrict to these subgroups or how they induce to this from the subgroup to the full group.
Is there any sense in which ST is the Weil group of GLT?
Yes.
ST minus 1.
Oh, ST minus 1.
First of all, in the stable limit, SLT and GLT are the same. Okay, there is no difference. But there is a certain sense that ST is a subgroup of GLT. I should have maybe mentioned this, that you can identify this Grothendieck ring, which is the direct sum of all R of Sn. You can identify this with the algebra of symmetric functions. Okay, and this is an algebra isomorphism. And the product here is the stable Kronecker product. But if you pull over the, take the simple objects in here and pull them over, you get symmetric functions. And this is a very interesting, I think, new basis of symmetric functions. It's non-homogeneous. But anyway, this, to answer your question, this is easily seen the Grothendieck ring of GLT. And therefore, there's an isomorphism. Therefore, in this sense, probably ST is the Weil group of GLT.
Any other questions?
If you had a morphism from object X to object Y, then you get some kind of a translation function on this representation.
What do you mean with translation function?
Well, I'm just trying to sort of do what Zelevinsky did for GL.
Oh, okay. Okay, so it's very good that you remind me of Zelevinsky. The thing is simply, you in for FQ vector spaces, you get on this side the representation theory of GL and FQ, n equals 0 to infinity. And Zelevinsky showed that this is a Hopf algebra. Now, if you do this construction, you still get a Hopf algebra not quite, but anyway, you get an algebra. But it's much more complicated. Zielinski used as product the so-called Harish-Chandra induction. While here the product is given by actual induction, stupid induction, GLP cross GLQ to GLP plus Q. And I think that the Lewinsky swing is a degeneration of this one. This here is much more complicated, and if you introduce some filtration, take the associated graded, then you get the Lewinsky swing.
Other questions? Okay, so let's thank the speaker again. And then, as